Okay. A 480 ohm resistor and an uncharged 1.5 microfarad capacitor and a battery are all in series. Let's draw the circuit. Battery is 6.11 volts. Resistor has 480 ohms of resistance, and then the capacitor is a 1.5 microfarad capacitor. All right, it's asking for the initial current, so for that we just want the full form of the current as a function of time will actually be I sub 0 times e to the negative k times t. Okay, why would it take that form? Because current is going to decay with time in an RC circuit. It's going to start up high. It's going to slowly decrease toward 0. The value that it starts at is called I sub 0, or the initial current. K, once again, is going to be the quantity 1 over tau, where tau is the time constant, R times C. All right, so if I rewrite the formula, we get this. And that's just like a general formula for exponential decay. This time it's not approaching a maximum, it's heading towards 0, so it has a little bit different formula than the charge had before. Okay, now what we can do is find the time constant and the initial current. So the initial current using the old formula will be voltage divided by resistance. That's when you pretend like the capacitor isn't even in the circuit. So we'll have 6.11 volts over 480 ohms. It's 0.0127 amps. So that's going to be our initial high amount of current. It's going to head toward 0 as time goes on. When it comes to the time constant, we can do 480 ohms, 1.5 microfarads. Looks like the time constant is 0.00072 seconds. So this one has a much faster time constant than the previous problem I did. That's because it has a much smaller resistance, so current is allowed to flow onto those plates much faster. Alright, so let's put in 12.7 milliamps and 0.00072 seconds for the time constant. Now we want to find the current after one time constant, so we can plug into the instantaneous current formula now. Okay. I, after 0.00072 seconds, will be the initial current times e to the negative 0.00072 seconds over 0.00072 seconds. Plug that into calculator. I'm getting that after one time constant, current will be down to 0.00467 amps. All right, now, after one time constant passes, it may not surprise you to know that the current will decay to 37% of its initial value. In the same way that the charge built up to 63% of its final value, because we're decaying, it's a little bit different. But basically what happens is it loses 63% of its initial value. So you subtract that, and then you get 37% left. So we can just check that real quick by taking 37% of the initial value. Should come out to the same. Yeah. All right, so it just shows how there's a difference between charge and current. Charge builds up, current drops off. If it wants milliamps, it wants 4.7 milliamps. All right, last question. What is the voltage on the capacitor after one time constant? Voltage will change with time as well in an RC circuit. But do you think it decays to 0 or does it build up to a maximum? What do you think? The capacitor is uncharged at first. When it's uncharged, the voltage across it is 0. But at the end, when the charges do build up onto it, like this, now it has voltage. Now it has voltage across it. It's going to have the maximum at the end. So you always, with these problems, just want to think about like what's happening physically in the situation. Is it a value that's building up, or is it a value that's decaying? For voltage, it'll be building up. So that means it's going to form the formula V max times 1 minus e to the negative t over tau. See, we use 1 minus when it builds up to a max, and we just use e to a power when it's decaying. So, yeah, for this one, it said that the battery had a voltage of 6.1. It had a voltage of 6.11 volts. So after one time constant, after one time constant, we'll put in 6.11 volts. That's the maximum that it can possibly reach. And then we'll do 1 minus e to the negative 0.00072 seconds over 0.00072 seconds. That'll give us our answer. I'm getting 3.86 volts. All right, so 6.11 was the max. And apparently 63% of that is 3.8 volts.